Let's consider propene-propane separations. Most of the available adsorbents are selective to propene, and therefore the desired propene product can only be recovered in the final vacuum blowdown stage. Here is a typical PSA scheme for propene-propane separations described in the paper by Khaligi. The 5 stages consist of pressurization, followed by an adsorption cycle in which propane is removed from the top of the column. The adsorption cycle is followed by a co-current high pressure purge with propene in order to remove any adsorbed propane in the pores. This is followed by a co-current blowdown step, and finally a countercurrent vacuum blowdown is used to recover propane of the desired purity. The product purity is dictated strongly by the amount of propane that is still present in the void volume and in the pores in this final countercurrent vacuum blowdown step. Therefore, it is important to have an adsorbent material that completely rejects propane into the gas phase and is highly selective to propene. One such material is chabazite, and that is the material also described in detail in this paper. Here's the structure of chabazite. Consists one unit cell of chabazite has 6 cages. Each cage is separated from an adjacent cage by narrow 8-ring windows. But the cage volume for chabazite is slightly larger than for DDR zeolite, but significantly smaller than for fluxes. Chabazite zeolite, suggested as an adsorbent for propene-propane separations, is a cage-type zeolite where adjacent cages are separated by windows which are 4.2 angstrom in this direction and 3.8 angstrom in this direction. Due to subtle differences in the bond angles and bond lengths between propene and propane, the ratio of diffusivity of propene to propane is a few orders of magnitude high, as reported in this paper by Ruthven and Reyes. And therefore, due to the high ratio of diffusivities, it is possible to construct a kinetic separation scheme for propene-propane separations. Let's look at transient uptake of a mixture of propene and propane in all silica zeolite. The simulations of the transient uptake were carried out using the unary isotherm data along with the diffusivity data from the paper by Khaligi. Let's have a look at the animation for the transient uptake. This is the surface of the particle. The red line shows the uptake of propene that has a diffusivity 5,000 times larger than the diffusivity of propane. Propene penetrates into the crystal and achieves supra-equilibrium loadings significantly higher than the loadings at equilibrium corresponding to the loading at the surface. Note also that for a 50-50 mixture in the gas phase, the loading of propane at the surface is larger than the loading of propene. And when equilibrium is reached, the crystallite of chabazite is richer in propane than propene. The spatially averaged component loadings are plotted here. In black are the simulations that include thermodynamic coupling effects, and the lines colored blue are simulations in which thermodynamic coupling effects are ignored, and the simulations are based on the assumption that the matrix of thermodynamic correction factors is the identity matrix. Taking proper account of thermodynamic coupling effects leads to significant transient overshoots in propene and the attainment of supra-equilibrium loadings that are about a factor 3 to 4 times larger than the value at equilibrium. Let's examine transient breakthroughs in a fixed bed packed with chabazite. The feed mixture consists of a 50-50 propene-propane mixtures operating at 200 kilopascals and 353 kelvins. Two types of simulations were conducted, shown by the black lines and the blue lines. The black lines are the simulations in which thermodynamic coupling effects are duly accounted for, and the blue lines are the simulations in which thermodynamic coupling effects are ignored. The y-axis is the dimensionless concentration at the exit, and the x-axis represents a parameter, that is Q0, the volumetric flow rate at the inlet, multiplied by the time divided by the mass of adsorbent. This is a convenient parameter to use in order to compare experimental data, say, of the dimensionless concentration in tubes of different entering flow rates and masses of adsorbent. There are important differences between the black simulations and the blue simulations, and these differences are largely with respect to the times at which propene breaks through. If thermodynamic coupling effects are duly accounted for, the propene breaks through later. This is because of the large overshoot in the propene loading that was demonstrated in earlier slides. The attainment of supra-equilibrium component loadings within the particle accounts for larger uptake in the fixed bed adsorber. Neglecting thermodynamic coupling leads to earlier breakthrough of propane and consequently also to lower recovery of propene in the countercurrent blowdown phase in the PSA operations. Therefore, the important message that is to be drawn from this comparison is that for kinetic separations, it's vitally important to take account of thermodynamic coupling effects, because the net result is a higher productivity of the component that is recovered in the blowdown section.